Okay, exercise 169, page 426 in the new text. This is about a missile fired from the ground, and I've sketched underneath the question what a graph of distance against time for this missile. This is not showing on the x-axis distance travelled, so it's not showing the path of the missile, but it's showing how the height varies with time. So this missile could be going straight up and straight down, or it could be going in the x direction, but then that would be a constant speed. And so we could actually get a path that looks like this with a constant horizontal speed added onto it. But this is just showing maximum height reached is 200 meters, and it's showing height against time as this missile travels through the air. And so you can see from this that it reaches a maximum height after 4 seconds, and after 8 seconds it hits the ground. What we need to do in this question is to show that the maximum height is 200 meters using calculus, and to confirm some of the other values we can get from this plot. So part A, find the initial velocity. So velocity is the rate of change of displacement, or x, with time. So the velocity equals dx by dt. So we've got our original function, and we need to differentiate it to find dx by dt. So we've got x equals 100t minus 25. 25 over 2t squared. So we need to differentiate it. That's the first step. To get dx by dt equals 100, t disappears, minus 25 over 2 times 2t squared. 2's cancel, so dx by dt equals 100 minus 25t. Sorry, this should be t, not t squared. So the initial velocity is the velocity when time equals 0. So at t equals 0, the x and t equals 100 minus 25 times 0, which is just 100. So the initial speed of the missile is 100 meters per second. Part B, what's the time needed to reach the maximum height? So first of all, what we need to do is recognise that at the maximum height, the x by dt, the velocity, is 0 at the maximum height. We've got an expression for the velocity, dx by dt, and that is 100 minus 25t. So what we need to do is set the x to t equal to 0, maximum height, then we've got 100 minus 25t equals 0. Adding 25t to both sides, 100 equals 25t, dividing both sides by 25, t equals 4 seconds. So the time for this missile to reach the maximum height is 4 seconds. What is the value of this maximum height? So what we need to do is go back to the original function and substitute in our value that we just found for t, which is 4 seconds, and that will give us the maximum height. So the original formula is x equals 100t minus 25 over 2t squared. So then t equals 4 seconds. X equals 100 times 4 minus 25 over 2 times 4 squared. 25 over 2 times 16, which equals 400 minus 2 into 16 goes 8. 8 times 25 is 200. So 200 meters is the maximum height reached by my missile. Part D, when the velocity, what's the velocity when the missile reaches the ground? Well, this is a symmetrical relationship. If we look back at the original function here, we can see that we've now confirmed that the point of maximum height is 200 meters here. And we've also shown that that happens after 4 seconds. We've shown it here. But if it takes 4 seconds to reach the maximum height, then it will take another 4 seconds to hit the ground again. So it's expected to hit the ground again in 8 seconds. Also, if it's going up with a positive speed of 100 meters per second at the start, we would imagine that if it comes straight back down again, ignoring air resistance, it would come down with the same speed of 100 meters per second, but in the opposite direction, minus 100 meters per second. However, we could also say, or we can calculate that, if we let t equal 8 seconds, then we should be able to calculate that speed as it comes back down using the speed formula. So going back to part D, we could say that t equals 8 seconds. We could work out what the speed is, knowing that dx by dt equals the speed, which equals 100 minus 25 t. And so that equals 100 minus 25 times 8, which is 100 minus 200, which is minus 500 meters per second. So we can show it that way too. But also, we can answer that part of the question just by saying it must be coming down with the same final speed as it started off with, ignoring air resistance.